look at today are just arrangements of circuits. Now, most circuits are combinations of these terms that we're using here, parallel and series. Okay, the term parallel and the term series are an arrangement of the resistors in the circuitry. Again, most circuits are combinations of these. We will look at parallel alone, look at series alone. And then in 20-3, we'll look at the beginnings of something that has both parallel and series. Okay, you can get an idea of what goes on inside of an appliance. For example, if you remember back, we talked about, like, we gave an example with a cell phone being charged, the amount of energy or the actual resistance. We talked about a toaster at one point, I gave a resistance value. Those values are like an aggregate or a net resistance of the whole thing. So inside of a circuit, what happens? The electricity flows into the inside of a toaster, it flows into the toaster. Now, if I had both of the toaster things now, what does it have to do? If I had both parts of the toaster down, so usually there's 4 slots for toast, right? In traditional toast, there's 4 slots. If I just push one down, both slices go down for one sandwich, right? And it has to heat up how many of these things? Yeah, at least 2 sets of heating elements that way. If I then push down the other one, it heats up another set of 2. So my guess, I haven't honestly taken one apart, is that a standard one, like a standard toaster that you're looking at, will be in series, but each of those will be paired in parallel. So the actual circuit will be series, but there will be a parallel branch here and a parallel branch here. So it's always going to be a combination. Now, before I go further into this stuff with appliances, you need to know what this actually means and physically looks like. So here's what I want you to imagine. Simplest way, before you look at the next page of the diagram, simplest way to remember series and parallel. For something in series, first of all, series means one after the other, right? In series. And you've talked about series and sequences in your math class already. And when you talk about a series, you're talking about like 2, 4, 6, 8, 10, right? You're talking about numbers consecutively, one after the other. Now, light bulbs or resistors that are in series are the same thing as if you had, imagine, a pipe, like here you go as an example. So you've got a pipe, and there's water. I use this example a lot because it's very easy to make an analogy toward with circuit. So you've got a pipe. Imagine there's no hole drilled through this pipe. Okay? Water is flowing through the pipe. It then makes a turn, flows through another pipe, makes a turn, flows through the last pipe, then makes a final turn, comes out below this, maybe like all the water gets pushed out to the ground. Okay? Now, that is one continuous flow, is it not? That is series. Parallel would be, imagine if I put, in this case, it would be a T. Like a T-joint. A T-joint takes this end and it splits it into 2 pieces that come out. So it literally looks like the letter T. Anytime you have a junction or a joint at certain locations, you're going to see that where literally one piece would clip onto the end and then 2 pieces would come out, or it could be a Y. The other one's a Y. It's T's or Y's. A Y would look like the letter Y. Imagine taking this and making this the bottom of the letter Y and split it. So this junction, if there was a cap on the end that split it into 2 different flows, that's called parallel. Is that clear what I'm saying so far? So if you see a junction or a split in the circuit, and you would look like the flow would kind of separate a little bit to each, if there's some sort of a junction where 2 wires come together and then split later, or split and then come together later, that's always going to indicate parallelism. If it goes from one bulb, out that bulb into the next bulb, out that bulb into the next bulb, and back to the battery, the wire never split. It just continued to each bulb along the way. That's series. But if I see that it goes out of the battery, the wire splits, goes into one bulb here, and then those bulbs come back together, that's parallel. Okay, so we're going to see that the actual setup looks like the lines are parallel, like geometrically parallel to one another, but what we're also looking for is some sort of a junction where there's a split. Okay, where there's some sort of a split. All right, with that said, let's take a diagram so you can see what I'm actually saying. Look at the series circuit. If you were to follow the flow of electricity in that circuit, the flow would be in one continuous path. It would exit the source. It would go through the bulbs. I don't know which way it would go because I don't know which side is positive or negative terminal, but it doesn't matter. It would exit the source, go through bulb 1, come out. Bulb 2, come out, bulb 3, bulb 4, and back. It never split. The current, the flow never split. It was continuous the whole entire time. Look at the word parallel. Is it obvious that I want to split it to you? Follow the path. Again, follow the path. The energy comes out of the source. It gets to this point right here. And what do you notice right here where that dot is? Let me zoom in so you can see this. If you follow this along the way, when it gets to right here, what happens? Yeah, there's your break point or your split. This is like the flow of water coming through and then the water splits. Part of the water goes here, part of the water goes here. So this current goes into this bulb and comes right back to the source. But part of the current splits. It goes here. Goes into this bulb, back in, and it joins back up, back to the source. Well, part of the one that went here split and went up here. And part of that goes into here and comes back. Well, the rest of it comes out here and comes back. But notice that these two rejoin here. These two rejoin right here. The current from all these rejoin with this current down here at the bottom. But you're seeing all these branches and you're literally seeing parallel lines. In a parallel circuit, you will see parallel lines. In a series circuit, you do see parallel lines also. So don't let that confuse you, okay? I'd rather you understand the idea of a junction. Yeah.
I found electrons always go which path has both these resistance.
It absolutely does.
They all just go to the right immediately to avoid
No, because each bulb will have a different resistance. So it depends on the bulb's internal resistance. If a resistor has a high resistance, much less of the flow goes to that. So you'll notice that if you want to measure the current in these bulbs, the one with the higher resistance will have the lower current. The one with the lowest resistance will have the highest current. Okay? These are going to have different currents in these. But here, the flow never gets split up. So we're going to see all those ideas that you even just mentioned there apply to our rules now. So let's start with series version. Okay, it's the easier version. Theo, read for us, just for current, please.
The series current. The current across each resistor is the same, like the flow rate of water into a pipe.
So think about with a pipe flow with water. If there's no branching off, the flow rate is going to continue the same way. Obviously, if there's declination, right, it would speed up because of gravity. You get some sort of an incline that's going down. The water would speed up. But imagine you're on a level surface and there's a pump pumping water through a circuit of pipes. The flow in those pipes would be the same if there was no branching in place, assuming no change in elevation also. So this is just like water flowing through a pipe. And if you go look at your diagram, and you don't have to go back, let's just draw a quick diagram up top. These are all in series because there's no branching off. Notice no branching off. I did not have to pick up my pen once to draw that circuit. I put my pen down and I was able to draw the whole circle without picking it up. That's another way of thinking about it. It's like a discontinuous function or a continuous function. Okay, this is a continuous function, if you will, or a continuous flow. So we know that it leaves the positive terminal and we go like this. So if the flow is not changing or splitting, it means that the current across each of these is the same. So we can write down the following. Can somebody explain that notation, please? What am I getting at, Theo?
That everything is equal versus
And what does the N stand for, Theo? Or why am I saying IN at the end?
infinite because it can be
As many resistors as you have. If you have 10 resistors, you sum together. When you say I1 equals I2 equals I3 equals I4, all the way up to I10. Okay? The first I in the beginning is the current of the entire circuit. So the current of the whole circuit equals the current through each resistor. Does that make sense so far? It's pretty logical. Okay, so you're going to use logic for this. A lot of this is just straight up, like, think about common sense. What would your intuition tell you? Voltage, and you can read, obviously, to see this, but voltage, think about the following. Think about the following. The voltage used by each resistor, I guess you could say, by each resistor, is called a voltage drop. That's the term for it, actually. It's called a voltage drop. So imagine you have a 9-volt battery hooked up to a circuit, and the first resistor uses 5 volts. So again, this is a 9-volt battery. How does the bulb light up? It uses the energy, right? It uses the energy. The voltage is the easiest thing that's analogous to energy. So let's say that the first resistor uses 5 volts. What would be left then for the next 4?
1 each.
Yeah, either 1 each or maybe like 2, 1, I don't know, a half, and a half. But what does it depend upon? It depends upon the resistance of each bulb. We're going to see in a moment when we do an example that the amount of voltage going across really depends on the resistance. If a bulb has a higher resistance, it slows down the atoms more in that area, which means it can use more of it, which means the bulb will be brighter. So the bulb with 5 volts of energy or 5 volts of voltage being used will be the brightest of these 4. And if I really wanted to draw bulbs, by the way, I should put circles around them. Okay, even though resistors and bulbs are resistors, but just to specify that these are bulbs. So the brightest of these would be the first one. The next brightest would be the second one. And I happen to make them go down in voltage. It could be the opposite. Okay, it could be flowing this way. Maybe the first one is the weakest, then that's just as weak, then that's stronger, that's the stronger, and then that's the strongest. It depends on the actual resistance of each. So the voltage is the sum of all the voltages. So the voltage supplied equals the sum of all the voltages. Do you see the difference between these two things? Current and voltage. Current is an equality identity. Voltage is a sum identity. Okay? Again, current is equality. Voltage is sum. You want the overall voltage of the circuit, you can add the voltage of each of these resistors. But if you want the current in the circuit, you can just find the current across any of the resistors is the same. Well, if the voltage across each resistor is the same or different, but the current is the same, what we're going to notice is the power is going to differ. Because remember, what's the formula for power? Power, P equals what? You know, electrical circuits, not work over time. Power equals what?
V squared.
V squared over R is one of them. What else though? I don't want to use that one for now. IV is the simplest one. And take a look. I, for each of these bulbs, are the same. They're all the same I values, but V is different, isn't it? So if a bulb has a different resistance than another bulb, not only is the voltage different for that bulb, the voltage supply at least for that bulb, but the power is going to be different as well. This idea is going to stem forth and continue in your lab, okay, with power. The third thing we want to look at is resistance, and for this we're going to derive the formula. So let's take a quick look. Remember first that Ohm's law applies to each resistor. V equals IR. To every resistor you have Ohm's law. Thus, for 2 resistors, this equation for voltage, right, look at the equation above. For only 2 resistors, we don't have to do V1, V2, V3, V4. If there's only 2 resistors, it's just V1 and V2. So this right here, if I look at this V over here is just simply V. This is going to become I1R1 plus I2R2. Why am I allowed to do that? Why can I put I1 and R1 in for each of these? Yeah. I mean, this is V1, and since V equals IR, V1 equals I1 times R1. Or V2 equals I2 times R2. But either way, for each resistor, you can apply Ohm's law for each of them. But here's the thing. We know something about the current, don't we? What do we know about the current in a series circuit? What do we know about the current in a series circuit? What do we know? Katie? They're all connected, good. More specifically, look at the very top, Katie, tell me. They're all equal. The current across all resistors is the same when it's in series. So the currents are the same. When 2 things are the same, what should I do with them? Instead of calling them I1 and I2, let's call them both I. Now what we're going to see here, at this point, is that we can factor I right out of the equation. Factor I, leave it in front please. We're going to get to a conclusion soon, I promise you. I can factor I out because it's the greatest common factor of both these terms. When I do so, I can get rid of this I by dividing. Divide by I. And that I is gone. And take a look. V was the voltage from the battery originally. Look, it was the V we started with up here at the top. Go all the way back up to the top if you have to. The V that we started with on the left side is the voltage from the battery. So this is the voltage of the battery. This is the current in the circuit. Well, what's voltage over current? Voltage over current from V equals IR. Voltage over current is what? Voltage over current equals, Alejandro? Resistance. So this, believe it or not, is like what we call equivalent resistance. So we're going to write down the following. Equivalent resistance equals these. Okay, the equivalent resistance, V over R. And I'm going to explain why we're doing this in a moment. But to generalize this, we could also continue and write plus all the way to Rn. And this is the general rule we're going to see. Here's what this is saying. If for some reason, in part of my circuit, I had two resistors that were in series, and one resistor was 5 ohms, and the other was 3 ohms, and they were in series, I could simply add the 5 and 3 together and replace them with an 8 ohm resistor. An equivalent resistor, which is the sum of the other resistors' resistances. Again, an equivalent resistance comes from the sum of these other resistors that are in series. And the reason you might do this is because with a simple circuit, you need each portion to be summarized or simplified. So you can get the overall resistance of the overall toaster, not each individual branch of it, but the overall resistance of what you might need, which you actually would need. Okay, so we're going to come up with a way to come up with the equivalent resistance by using this rule. So let's see what we're talking about. You have a 9-volt battery connected to 4 bulbs as shown in the right. We want a schematic. We want the equivalent resistance, the current in the current in the circuit, and the voltage drop across each resistor. So we look at this diagram and we think right away, is this parallel or is this series? It's quite easy because we're going to talk about all day. When you look at the diagram, why is it parallel or series? Which one is it and why? Feel?
It's a series.
Why?
There's no change in the lines as it continues.
Yeah, there's no branching off, is the way to say it if you want. So we know that the flow is going to go like this. Through the bulb, to the next bulb. 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 Or to the back to the battery. Recharge, and do it again. Okay? Now, to draw a schematic of this, it does not matter. Draw your own, please, first, and then I'm going to draw mine. Yours will most likely not be the same as mine. Draw your own first. Okay? It doesn't matter if it's the same as your partner. All that matters is that you have a battery and 4 resistors all in series. It does not matter if you put 3 branches or 3 resistors on one branch and one on the other, but try to make it a rectangle, because that's traditionally the way you draw circuits. Let's see. Who should I call on randomly? Leave your hand up so no matter. Go ahead, volunteers. What did you draw yours like?
I just drew do you want me to show?
Just hold it up.
So I drew this.
Okay, is the battery on the left?
The battery is this thing.
On the bottom, got it. So Theo drew a battery on the bottom. It looks like he drew a resistor on the bottom legs and the sides, but not the top, correct?
Yeah, no top.
That works. Okay, there's 1, 2, 3, 4 bulbs. That works. I could have also just done this, right? Look. I could have done this. and put that bulb there instead. Do you see what I'm saying? All that matters is that these are in continuous flow. It does not matter if I had all 4 bulbs here and then I have empty wire. I mean, it wouldn't realistically be logical to draw it that way, but you could. Okay? You could. So what we're going to see here, obviously, is that the flow exits the positive terminal and goes through these batteries. So let's make believe this is the positive terminal in our diagram, just for the sake of directionals, and this is the negative. So we'll call this 7 ohms. This is our 5 ohm. This is our 4 ohm. And this is our 2 ohm. And the voltage supplied to the battery is 9 volts. Here's our diagram right there. It's the first part of our schematic. Now notice right away, and this is going to happen, we're going to see this in our lab, and we're going to see this in the rest of this section also, that the goal for any circuit is to simplify it into one single resistor. So in this case, the second step says, then find the equivalent resistance of the circuit. You've got 4 resistors in series. What does your resistance law tell you? What does your resistance law tell you? It's written in front of you on the previous slide, if you don't remember. What does the resistance law tell you about this? What do we got? REQ equals what? REQ equals what? Katie, go ahead. No further, obviously, right? 4 bulbs, 4 resistors. We simply sum them together. Summing these 4 together, what do we get?
18.
So that's the equivalent resistance, which means, really, I could do this. And it's the same thing. So I can simplify all 4 of those bulbs or resistors into one simplified resistor of 18 ohms. I'm stepping you through this problem because the next part you have to use what we just did. The next part says, from this, determine the current in the circuit. You want the current in the whole circuit. Well, what's the voltage of this battery again? What did we say, 9 volts? So the voltage in the whole circuit is 9 volts. The resistance in the whole circuit is 18 ohms. So this is the overall resistance, the overall voltage. That will give me the overall current if I use V equals IR. So I solve for I by taking V over R. V over R is going to be 9 volts over 18 ohms. Give me a current of 0.5. So what we're noticing is this. We were able to determine the current in the entire system because of the equivalent resistor. Because of the equivalent resistor. There's no other way to get the current. Okay, if you want to get the current in the entire system, you need to know the overall resistance. Plug that in here. You know the overall voltage. Divide these two, you get yourself the current. Now, what you also could check right now, what we're going to look at is this next part that says, from that information, calculate the voltage drop. Well, voltage drop means how many volts are being used by each resistor. If I want voltage, Ohm's law tells me V equals IR. So if I want the voltage across the first resistor, I have to take the current through the first resistor times its resistance. Well, the first resistor was 7 ohms. I know that. The second one was what? What was it? 7? Let's see. 7, 5, 4, 2. So the first one's 7. The second one was 5. And then 4. And then 2 afterward. What about the current? What about the current? What am I going to plug in for these 4 blanks? How much current is going through each resistor in this problem? How do I know? How do I figure out? What do I do to determine what I'm going to use for current for each of these? What am I going to do for current for each of these? Look at your notes, people, please. Go back up, scroll up. Look at your rules for current. What does current tell you in series? Ellie, what does it tell us?
Current across each resistor is the same.
It's the same because there's no branching off. So the current in the system is 0.5. That means it's the same for each resistor. So in the end, this is just going to be 0.5 amps for each of these. It's not changing. Again, the current in series is the same. So just take half of the resistance to get the voltage for each. 3.5, 2.5, 2, and 1. 3.5, 2.5, 2, and 1. So some of these bulbs, because they have higher resistances, are going to use more voltage. Those bulbs are going to be brighter. They're going to be brighter. What else makes this answer, or what else validates those 4 answers? Figure it out. It's not obvious. What else validates or makes you feel comfortable about those 4 answers you just got for voltage? 3.5, 2.5, 2, and 1. Joe, what do you got?
Well, when you add up the voltage, you get 9 volts.
Yeah. Look at the rules of voltage. The rules of voltage tell us the overall voltage equals the sum of all the voltages. That was in the last slide. So what Alejandro did was he said, you know what, 3.5, 2.5, 2, and 1, add those 4 voltages up. You get 9 volts. You get 9 volts. Okay? Alright. Is it be there, right? Right? For 5 minutes?
Yeah.
Okay. Let me quickly show you something. Instead of starting parallel, what we'll do is we'll do parallel tomorrow, and then we can hopefully get the lab done. This is pretty much 3 periods total between this lesson and the lab. And I'm going to show you something because we have a little bit of time left. Pablo, there's an orange tool back there. Can you get it for me? It's got wires connected to it. Thank you. So you're going to be working with these over the next 2 days, or maybe in 2 days, depending on, I don't have you guys tomorrow, so maybe in 2 or 3 days. And when you connect these, so you can see what it looks like, you have your positive and negative terminal, positive and negative terminal. You don't have to use these clips up here, these alligator clips. Okay, there's rubber on the outside. Why? Yeah, so you don't have any electrical current going through you, going her, going one in the front. This is very 1.5 volts each, very small. I exit one battery, let's say I'm going into this bulb. Okay, exit the other bulb. And what's going to happen when I touch this battery? What should happen? It's going to be very dim though, because these are very weak batteries, but you can still see it lighting up. Everybody see that? When I touch this? Okay, I can put my switch in here as well if I wanted to. So the switch is exactly what it sounds like. It's a switch, so when I connect, it doesn't work. When I push down on this button, it works. This button, when I press down, allows 2 metal contacts to make contact. When you push down, it closes the circuit. When I let go, it opens the circuit. This is your switch. Okay, do you see your switch when you press it? Now, if I were to string a second bulb into this, so if I were to exit, I'm trying to do this properly. If I were to exit the one bulb, I exited the first bulb and went into the second bulb instead, like I'm doing here in this diagram, right? So I'm exiting bulb A, I'm going to go into bulb B, then I'm going to exit bulb B, and go back to my switch. What do you think is going to happen now that there's 2 bulbs in place when I try to turn this on? Yeah, they're going to be both weaker. Why? 2 bulbs, each bulb gets part of the voltage. Remember, the total voltage equals the sum of them. So when I press this down now, you can barely see the brightness. Up here you can probably see both, right? But you can barely see it when they light up. Okay, the brightness decreases significantly because the voltage is now spread out across both of these. Well, on the battery? If I include the other battery, the voltage, the brightness will go up in both, for sure. And I'll show you that in a minute. This is a voltmeter or an ammeter, or also known as a multimeter. You can measure voltage, you can measure current, you can measure resistance. So if I take this, and I have it on the 2 voltage setting, I can do 2 volts, 200 volts, I can do 0.02 volts, and that gives me the maximum. Since I'm looking at 1.5 volt batteries, I don't have to worry about going over 2 volts, so I have another 2 volt setting. So when I connect this across the battery alone, and across the battery, what are you seeing right there? This decimal.
1.5.
What do you get set on? Exactly. 56? 1.56 volts. These batteries are made to be 1.5 volts. But remember that even though it's written as 1.5 volts, there's probably a little bit more power in it because that's what you're really going to get is 1.5. And once it goes through your circuit. Now, if you want to just push this down, the switch. If the switch is pushed down, part of the voltage is going to go to each battery. So let's see, or each resistor. So let's see what we get here. For this one, we're getting, so let me write this down. 0.6, yeah, 0.7. Let me just remember, I guess. 0.7 for that one, and for this one, 0.6. So it looks like when we actually connect this to the switch, there's probably internal resistance in the switch. So the switch is actually probably carrying some of that voltage. Because this was 1.5 volts. Yet we got 0.7, 0.6, which only adds up to 1.3. So there's loss of voltage. Remember we talked about this? There's like that EMF, we talked about that term. So the battery itself has a little internal resistance. The wires have resistance. The switch has a little bit of resistance. So there's some voltage loss to the other elements in the circuit. So when you sum these 2 voltages together, you don't get exactly 1.5 that you started with. Okay? Does that make sense, the idea? So you can use this to measure even current. Let's go to current. Yeah, I'm going to try this in class. Yeah, want to hit that again? There's literally like there's no current going through here. It's very low, it's not even detectable. So your multimeter is good to use around like the house. If you need to figure out if there's a shorted circuit somewhere, and you want to know if there's voltage supplied to something, why it's not working, believe it or not, these are the things you would stick into an outlet. You can literally go to an outlet, stick one in one end, one into the other, and you
I still wouldn't do it.
No, I don't really watch. So this is a setting for up to 200 volts. This is only 120 volts. So what I'm going to do, guys, again, look, this is rubber and plastic. I'm not going to get zapped. If you did this with 2 pieces of metal, you'd get zapped, right? But if I just stick this in the outlet, it should work. Now, depending on how deep these outlets are, this one might not work. But if you take the cover off, you can actually touch the metal pieces in there directly. Let's see if this actually does.
Oh my god!
That's scary.
Just kidding.
That
It would
was
have been a lot
so
louder on the
good.
screen.
I thought you were just like convulsing.
No, I was just messing with you. Let's see. It's not touching the metal contacts, unfortunately. Hold on. If I angle, maybe here. If it jumps up to like 100 and then it drops back down, it's not actually touching the metal pieces. Maybe this outlet is loose. Yeah, this outlet's a little bit loose. Now, I gotta do makeup. You know what I'll do? At home, I have an outlet that's like an old one that doesn't have the cover, that's exposed. I'll try and do that and take a quick video to show you what it looks like. Okay? But I gotta see. I don't know if it's gonna work or not. Hopefully it will. But you can literally touch the 2 wires. The easiest thing to do. So if you've ever looked at an outlet before, take an outlet, the casing off there right here. Once you take this off, this piece, what's that?
We just connect it to the wires.
Yeah, this piece here, literally, once you take these screws out, this piece, you can pull it out. You can pull it out, you'll see 2 wires leading to it. The 3rd wire will be the ground. You attach it to those 2 lead wires, you'll get the actual voltage. Okay? Hey, the recommendation, start with the homework. Whatever you can get done, do it now. Okay? Because if you can't do it all yet, you can do everything in series. So at least do stuff in series with homework.
Not do tomorrow.
No, because we didn't finish this lesson. I don't see you guys tomorrow, right?
Yes. you have a favorite player?
I was like in the chess club and stuff. I was actually very good. But you could start a chess club. Doesn't matter. They're in the library, they're here. Either way, I'm out of game. I'll maybe like 2 minutes. So just drop it off and you know.
Okay.
You know, not mine. And class, if for some reason you need to bring it back before the school is closing or people are leaving, just take pictures of the problems at least. You know what I mean?
Yeah, I'll probably be done with it like half an hour.
Yeah, so just bring it back up, open the door, grab back in. Okay? I got to like 3 or 4 pages of everybody so far. Come tomorrow office hours. Hope that I'm done tomorrow. Hope I have a game tonight and then I have to tutor tonight. So I'm gonna be at school until 9:30. So I don't know if we're gonna do grades today, but I'll try. Okay, we'll come to office hours tomorrow either way. What we notice in series, and you know this about a lot of old Christmas lights, there's like a really corny song, you know, the 12 Days of Christmas, there's like a parody on that song, the 12 Pains of Christmas. Pains, like the headaches that Christmas brings upon you, like sending Christmas cards and this and that, and like dealing with like, you know, family members that might not be very nice people, whatever it may be, right? So there's a song called The 12 Pains of Christmas, and in the song, you hear the guy in the end, he talks about like stringing up the lights outside, how much of a headache it is to do that. And they say in the middle of the song, one goes out, they all go out. And this is what he's talking about right here. When lights are strung in series, if one bulb goes out, all of them go out. Because the circuit is now open. When that bulb dies, suddenly that charge, although it's being pushed forward from the positive terminal, it cannot go continuously through here. It can't just jump that gap and end up over here. So because there's a break in the actual circuit, that's like an open circuit. So in series, if something either burns out, whether it's a bulb or a resistor, the entire circuit itself will stop operating. This is in series. So you can see the limitation to a series circuit already. If you have something like this, you realize that if one thing breaks, the rest of them aren't going to work. Now, a lot of things are not just in series, but they're in series and in parallel. They're combinations of both of those different circuitry setups. And we're going to see a lot of that combination in the next section, but for now, we want to take a look at parallel. Theo, you had your hand up beforehand, sorry.
I was just going to say, that.
Oh, you were going to explain this. Okay. I'm sorry. So in parallel now, think about the diagram we drew for parallel circuits the other day. A simple parallel circuit looks like this. Here's your battery, leaving the positive terminal. Here's a resistor. But each of these branches off. Or maybe it even looks like this. Like there's another way of drawing this. You could draw it like this. Where this wire continues, it branches off. Okay, so you could draw parallel circuits in many ways. Those are all examples of parallel circuits right there. You have 5 resistors. 3 of them are set up in parallel with each other. And then there's a little subset of 2 of them in parallel by themselves. So in parallel circuits, the first thing I want you to recognize is that there are locations along the wire where the wire splits. When you see some sort of a split, think of parallel right away. When you see that split, think of parallel right away. And in addition to that, think of the fact that the current is not traveling only in one flow anymore, through one pipe, if you will. The current, or like the water flowing through a pipe, branches off in 2 directions. So part of it gets one part of the current, part of the other branch, or the other branch itself gets part of the current. So right away, look at the first law. The first part about current tells us the sum of the currents across each resistor, the sum of those currents across each resistor is equal to the current leaving the battery, the sum of them. And that makes sense because if you think about it, if I have, let's say I have 5 amps of current coming out. When I go here and it splits, this resistor might only get 1 amp, and the other 4 go here. Well, the 4 that go here, maybe 2 go here and 2 go here. Out of the 2 that goes here, maybe like 1 goes here, and then the other one is split between these 2. So the current or the flow rate branching off splits up every time. So if you want the total current in the system, you could sum together all of the currents. This is not the same as when it was in series. In series, the current across each resistor was always the same. Here, though, we know that the current in the overall system is equal to the sum of the currents. That's all that means, okay? The sum of the currents for each resistor equals the total current supplied by the potential difference, by the voltage, by the battery. Okay, it's a sum law, whereas when it was series, it was not a sum law. In series, the current is the same across each resistor. I1 equals I2 equals I3 equals I4, etc. But here now, instead of an equality, we have a sum law. Now, for voltage, we're going to think now to this point. For voltage, we're going to think, well, you know what? This is the positive terminal. It's connected to this resistor. This is the negative terminal. It's connected to this resistor. Well, this positive terminal is also connected to this resistor and this one here. And the positive connects here, and the negative connects here. Now, here's a little bit of a different case. We'd have to simplify this. But for these three alone, we could say that since these are in parallel with the original battery, the voltage supplied to each is the same. Because the positive terminal connects here, it also connects here, it also connects here. We don't have to worry about as the voltage or as the circuit goes across each resistor, there being a drop in voltage because of the fact that the positive terminal is connected to all three resistors. The negative terminal is connected to all three resistors. So these three resistors in parallel with the battery all are given the same voltage. This is a different situation. We'll talk about that in 20-3. But the idea here is that with voltage, the voltage across each resistor, is the same. So what could you say about current and voltage? What could you say about current and voltage in parallel as opposed to the current and voltage in series? As opposed to series. Look back at your series laws. Look at the laws of series. Go ahead, Nat. Yeah, it's the exact opposite for parallel. In series, if you remember, the current was an equality the whole time, whereas now we have a sum. In series, the voltage was a sum, whereas now we have an equality. Is that clear? So they're really switched. Now, you don't have to memorize these laws. If you need to, go ahead and look at your formula sheet right now just to verify that. You're going to see that there are 3 laws in series, 3 laws in parallel. I put S for series and P for parallel kind of to help you. Okay, but the idea, what you want to remember, is the actual fact that these are switched. Now, it's also important to understand the theory behind this. The reason why the sum of the currents add up together to give you the total current of the system. Because in parallel, the branching off indicates that the current is also splitting up. Now for resistance, we're going to have to derive this again, which is a little bit trickier than the one in the past. So we're going to start again with Ohm's law here. We're going to start with V equals IR. And we can rewrite V equals IR. So we can start as I equals V over R. Now, this comes from up here. In parallel, the current of a system equals the sum of the currents. Let's look at a 2-resistor circuit. So in a 2-resistor circuit, we start with this statement. Now, in the series setup, we did something to make this look a little bit easier. What can we do in the parallel setup? We're trying to derive the resistance. We're trying to derive the resistance. What can I replace I1 and I2 with? Yeah?
V over R.
What is it?
V over R.
Yeah, V over R from right here. I is V over R. See it circled on the left there? So replace I1 with V1 over R1. Because that's what I is V over R. Well, again, we have V over R, but instead of 1, we put a 2. Now, the overall current of the system is going to always equal the overall voltage over the overall resistance. Well, that's called the equivalent resistance. Remember how we took those 4 resistors and replaced them with 1 resistor in that example we did? Same idea here. The equivalent resistance is what we're searching for. We're trying to determine what the equivalent resistance is. Now there's something else that we can utilize to help us simplify this. What is it? What can we do to help simplify this? What can we do to help simplify? Because I'm not really done. I don't really want voltage. I want to deal with resistance. I don't want to deal with voltage. There's another piece of this problem that tells us about voltage. I purposely didn't move the slide up too far so you can see the very top. Ellie? The resistors? Not the resistors. The voltage supplied to each resistor is equal. The voltage supplied to each resistor is equal. So that means that I can replace voltage where we see V1 and V2 with just V. The voltage supplied to the circuit is equal to the voltage across each resistor. So those are really all just V now. And then I continue. What can I do to simplify this? What can I do to simplify this? Katie?
Can you cancel?
Yeah, it's in every term. When something is in every term, you can cancel them all. If you don't think that that's true, let me show you. Factor out of V, this becomes 1 over REQ. Factor out of V, this becomes 1 over R1 plus 1 over R2. V's on both sides, isn't it? So as Katie mentioned, we can cancel V on both sides, leaving us with only terms of resistors or resistances. Now if I had an infinite or n amount of resistors, I would continue this formula and just put this, so I'm just going to continue it. However many resistors we have, this is the law that we're going to use. How is this different from series? How is this result different from the result we got when it was in series? Come on, it's obvious. I'm seeing the same 2 hands a lot. How is this different? Go back and look at your series answer if you don't know. Scroll up, look at the series answer, compare it to this. Compare what you see in series to this. Emma, go ahead.
It's not 1 over.
Exactly. It's the only difference. These are reciprocal sums. It's 1 over, whereas the other ones were just sums. So in series, you would just literally add up all the resistors. You've got your equivalent resistance of the circuit. Here, though, we need to sum together 1 over the first resistance plus 1 over the second resistance. Now remember that that does not equal the equivalent resistance. That equals 1 over. So in the end, we're going to get all these fractions here, right? We're going to have to add together all these fractions, come up with a fraction overall, and then invert both sides to get R and Q by itself. This is 1 over R and Q. This is not R and Q. So we're going to have to flip this side eventually. So eventually we're going to have to flip this side, and we can't flip these individually, or else then you just go back to series. Okay, you have to add up all those fractions first on the right-hand side, and then take the inverse or reciprocal of the system.
So if the resistance was 5 on the series, would it be 1 over 5 in parallel?
Well, you need more than 1, remember. So if you have several resistors, yes, it would be 1/5 plus 1/7 plus 1/5 plus 1/8. You'd add up all those numbers, you'd get a fraction. That would be 1 over this, so you would invert both sides to get the actual answer. We're going to do an example now, so you can see it. Okay, but the idea here is that the difference is these are what are called reciprocal sums. Reciprocal sums. Okay, whereas in the series arrangement, those were just the sum of all of the resistances. Now, notice please, it's the exact same example, except I've set up the circuit or the diagram here, the setup, in a different fashion. Okay, what we're seeing here is this. Let me give you a quick demonstration of this so you can see what's happening. So what we're seeing in this example is a battery. Okay, so this is a simple circuit board, just to practice for like a physics class. So here's your battery. These are a bunch of different resistors here. These are your 3 bulbs. Here's your switch. This is a potentiometer. This is a capacitor. This battery could be connected here from the battery to the first bulb. Now, I could simply come out of the first bulb, connect it into the second bulb, and then come back to the battery. And this would be series. This would not be parallel. Okay, because look, again, the first bulb gets connected, you're going to see very little brightness here. You're barely going to see it actually, because this one battery is not enough to power both. So you're going to see that this is connected here to the first bulb, which is then connected to the second bulb, and then the second bulb is back to the actual battery. But if I wanted to do this in parallel, remember, take a look at the diagram. Out of the battery, I can actually point on here. Out of the battery gets connected to the first bulb. From the first bulb, though, you'll see a wire connecting to the second bulb. It branches off. That wire branches off to the third. That wire branches off to the fourth. And the same thing happens on the other side. So here's what this would look like now. The battery connects to the first bulb right here, and the first bulb branches off. Instead of going through the bulb, instead of the circuit going through the bulb, coming out on this side, hitting here, instead of that happening, this first bulb itself physically branches off into the second bulb right here. This is the branching off right here. See how these are both connected to the same bulb? This is showing a juncture where they separate. And then on the bottom, on the bottom here, the second bulb then connects back to the first bulb. But we're going to see that the first bulb, to be in parallel again, can branch off from there and connect back to the actual battery. Okay, and we see a little bit more brightness here. We see a little bit more brightness in these 2 bulbs. So when you do this lab, you're going to take a look at arrangements of parallel and series that are honestly pretty simple. When you're done doing the stuff in the lab, what I want you to do is just kind of tinker with it. Try different arrangements. See what affects the brightness of the bulbs. Try to work the potentiometer into the system. You're going to have to work the switch into the system also. Study the back of this, understand where these nodes all go. Yes?
What's the capacitor do?
The capacitor is able to charge. So a capacitor stores energy. So if you need energy in a circuit, for example, my guess would be that a generator has a capacitor in it. It's similar to a battery, but it temporarily stores energy between 2 magnetized plates. So one is positively magnetized, one is negatively, and it's able to store the energy between them. We might, I don't think I'm going to do anything with capacitance, but you could research a little bit further. A lot of the laws of capacitance follow these laws that we've been talking about with current, voltage, and resistance. They're similar. So let's take a look at this example here. A 9-volt battery is connected, as shown on the right, which is parallel. Draw the schematic for this. So go ahead and draw yourself a schematic. Use the example we did on the last slide as your example here if you'd like to. For this arrangement, there really is only one way to do it. You could kind of vary that one way to do it, but for the most part, for parallel, there's one real answer for this. Whereas for series, if you remember, there are many ways to draw it in series. So you could have a variation of what I'm going to draw, but you need to have each of the actual terminals or sides or ends of each resistor connected to the battery, really. So here's how I think about it. Start with the battery, connect it to one resistor. Now I need that battery to connect to the next resistor. The only way to do that is to branch it off some way. I could branch it off like this and draw the second one like that. Is that what you're going to do, Theo? Sorry, I missed your hand again. I could branch it off again the same way for the third bulb, and again for the fourth bulb. This battery has a voltage of 9 volts. The resistors are 7 ohms, 5 ohms, 4 ohms, and 2 ohms. The exact same resistances as we had in series. I made this example, and actually I think this figure is either out of your book or I pulled from somewhere, specifically so that you could see the comparison between series and parallel. These are the exact same 4 bulbs that you had a moment ago. Again, the exact same 4 bulbs. So from this schematic, what we want to do is find the equivalent resistance. Equivalent resistance. Well, these are all in parallel. They are no longer in series. If they were in series, what could we do to the resistances to find the overall resistance of the circuit? If they were in series, what could we do? Resistance. To find the overall resistance or the equivalent resistance, you could add them together if we're in series. But as Emma told us a little while ago, these are 1 over. These are reciprocal sums. We can't just add them together. So we have to use our reciprocal sum identity, which tells us 1 over the equivalent resistance equals 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3 plus 1 over resistor 4. You can see right away that you cannot just add together 7, 5, 4, and 2 and get 18, because these are all fractions. How would you add this in math class? Yeah, but do you want to do that for this, honestly? It doesn't look very easy. Common denominator here would be 140. It's a mess, right? You would not want to make 140 a common denominator. So here's what I suggest you do. Take out your calculator real quick. Add together all 4 fractions, please. Add together all 4 fractions, please.
I have 1.092.
Yeah, that's the decimal. Very good. That works. We don't even need a fractional answer here. 1.09. Please do this, even though I know I just put the answer. Do it, but I want to show you the next time. So type in your calculator, get an answer, wait. Get the 1.09 and wait. Now, if I want to know what REQ is, all I need to do is flip the left-hand side, and I get REQ by itself. But if I flip the left-hand side, yeah, you got to do it to the right-hand side. It's the same thing as switching these 2 spots, isn't it? Look, if I switch these 2 spots, I get 1 over 1.09 equals REQ. And that's the same thing as flipping both sides. So you could do 1 over 1.09, or just hit x to the negative 1. On your calculator, there's a button that says x to the negative 1. X to the negative 1 is 1 over. You learned this in your math class, that a negative exponent means a positive in the denominator. So really, to get your answer, it's just that. That's all it is. Okay, which is the same thing as this. Those are identical, same exact thing. And what do you get when you do either 1 over 1.09 or just 1.09 to the negative 1, Ellie?
0.94.
0. Which one is it? 92. And my units are ohms. Those are my units of resistance. Pause for a second. Scroll back to a series example. Scroll back to the example in series. What was the equivalent resistance in series? What was it? 18. Because we just added the 4 resistors together. Yet, in parallel, it's not even 1. It's not even 1. So let's write a little note down.
So in general, we would parallel this have much less resistance.
Yeah. If you want to achieve a circuit with low overall resistance, use parallel. This is why I kept saying, like, it depends on the scenario. Some things are all parallel, or a mix of parallel and series. Who knows? Some things are all series. But in a certain spot in a circuit, or a certain loop in that circuit, if you want to have a very low resistance, put everything in parallel. What does a low resistance cause? What does it cause?
More efficiency.
Okay, not necessarily more efficiency, but something more direct than that. It's more simple than that. A brighter light, okay, because it does use more of the energy, yes, that is true.
Maybe like it would like short circuit.
It could short circuit. Why, Emma?
Because since there's no resistance, energy's going
Yeah, when there's very low resistance, you have high current. When you have high current, that energy is just able to flow without slowing down. So a parallel circuit also causes a high current. And let's do that. Let's figure out the current right now. What's the current? How do I find the current? V equals what? What's Ohm's law? V equals? IR. Well, we've got R. We're looking for I, aren't we? The voltage supplied to the system is 9 volts. The current is what we're looking for coming out of the actual source. We've got the equivalent resistance. That's going to be 0.92. Okay, remember, this is for the system. This, I'm looking at Ohm's law for the overall system. The overall voltage is 9 volts. The overall resistance is 0.92. For a current, what do you get? What do you get for a current here? Simple math, right? What do you get, Dro?
We get 9.7.
When you round, is it 9.8 or 9.7?
9.7.
I think it's 8, so just be careful what you did. It should be 9.8 amps. What was the current in series? Scroll back up. When you did this problem in series yesterday, what was the current? 2 days ago. 0.5. So in series, you got high resistance but low current. In parallel, you got low resistance but a higher current. You all see what I'm saying here? So again, depending upon the scenario, depending upon the application, things can vary. Your arrangements can vary. Your arrangements should vary as a result. The last step, what I want to do here, is go ahead and calculate the current through each resistor. We know that in series the current is the same through each resistor, but we're in parallel. So if I want to look at each resistor now, I'm going to find the current through each resistor. How do I figure out the current through each resistor? But here's the thing, Ant. We've got R1, but what's V1? Why?
Because everything is the same voltage in a parallel circuit.
Look at your parallel circuit law. V1 equals V2 equals V3 equals the voltage from the source. The voltage across any resistor is equal to 9 volts in this setup because it's in parallel. In parallel, all voltages are the same. So this becomes a pretty easy problem to solve now. We're going to get 1.3 amps. For the second one, you still have 9 volts over 5 ohms, giving us 1.8 amps. And then the third is 9 over 4, 2 1/4 amps. And then the fourth is 9 over 2, 4.5 amps. What do you suppose is going to happen? Look at your current law for parallel. Look at your law and current for parallel circuits. Parallel circuits. Now, what will happen here?
You add them.
And okay? What are they equal? If you add all these four automatically, what will they be? Yeah, 9.8. Why 9.8? was 9.8? Huh?
Was it like the battery magnitude, little wire you lose kind of the voltage because it goes on to be more amperage in the battery?
So the battery itself provides the most current amperage, the most current, and you lose that as it branches off, exactly. So each of these different branches gets a piece of the current because it's splitting up. And if you sum these four together, you should get back to around 9.8. You round it a few times. Okay? Hopefully it's almost exactly 9.8, but it'll be near that. Okay, so again, the sum of the current across each resistor, or currents across each resistor, equals the total current provided by the battery. The current provided by the battery is 9.8. You get that when you sum those four together. Before the bell, we're gonna do the lab tomorrow clearly. Before the bell rings, let's take a look. Let's take a look at this. Do we see why? Do we see why in parallel? Take a look. If one bulb goes out in parallel, I'm just going to cover this bulb up. Let's say this bulb goes out right here. Okay, that bulb is no longer there. When that bulb blows out, the circuit is not open. It still continues. Watch. If I were to follow the flow out of the positive terminal, it goes in this bulb and back in. It goes in this bulb and back in. It bypasses right here. Goes in this bulb and back in. It goes in this bulb and back in. This just gets bypassed. So in parallel, if one bulb goes out, the rest still work. Or if one resistor fails, the rest still work. Okay, let me show you a quick example of something we're going to do in the next class. Well, actually, in the second period of tomorrow, we're going to do this. If you have an arrangement like this, what setup is that? Why is that series? They're all connected, there's no branching off. How about now? How about now? It's both, very good. These are Christmas lights, new Christmas lights. If you notice, if a Christmas light goes out, about 5 or 6 sometimes go out around the area of it, it's because you have a bunch of little series circuits that are parallel together. Okay, that's physically what's happening here. So one bulb goes out, you see a strand of 3 or 4 go out, but the others all remain. So if I take out one of these bulbs, literally right here now, I take out this bulb right here, that entire circuit area goes out. But the rest are still good. Those are all good still. Okay, to summarize, okay, recognize please, don't worry about the diagrams at the top, I already showed you the diagrams. But recognize this please, look. I and V switch. For series, you have an equality. These relate to each other, and these relate to each other, and these you got to know. Please do this homework tonight. This homework will be tonight.